History of Vector Analysis, Episode 7, Quaternions, Part 1. You are here. Hey, Soul Dog Goaler. Welcome back. This is going to be the first part of a two-part episode on the definition and properties of quaternions. Previously, I introduced William Rowan Hamilton, a brilliant but overly metaphysical guy who sought to grasp the mysteries of the universe by extending the complex plane into three dimensions. Hamilton presented his initial work on triplets, he and others had referred to complex numbers as doublets, in 1837. His primary problems were with the multiplication of triplets. Among other things, he couldn't get them into the right form, that is, of another triplet. After a solid 6 years, in 1843, he presented his workaround to the Royal Irish Academy. His solution was to introduce a third imaginary axis, extending the total number of axes to 4. The work is, in fact, pretty brilliant, even though its hyperspatial 4 dimensions seems contrary to the motivation behind proposing a third axis in the first place, that, the real world is three-dimensional. But Hamilton and we will have to return to that later. Rather than take you through Hamilton's derivation, even if I could, I will instead present it the way Hamilton himself did, as a brilliant flash of insight. Let's begin with the question, what is a quaternion as a mathematical object? I will use the compare and contrast approach. If complex numbers are z equals a plus ib, and triplets are t equals a plus ib plus jc, then quaternions are a plus ib plus jc plus kd. For a total of 4 components, hence the name quaternion. I will use a color code for the letters I, J, and K as red, blue, and green going forward for clarity. As was the case with triplets, Hamilton chose/discovered that I squared equals J squared equals K squared equals -1, but that I is not equal to J is not equal to K. With triplets, Hamilton's problems began when he tried to determine what the products Ij and Ji should be, and he never could come up with an answer that led to internally consistent results. The trick with using 3 imaginary axes instead of 2 is that now you have another option. You can try Ij equals K. This, it turns out, works spectacularly, although not perfectly well. Of course, more is needed. There are 6 combinations of unlike letters that need to be defined. Hamilton's discovery, if you want to call it that, was to recognize the 3 cyclic products, the ones in IJK order, as positive, and the 3 anti-cyclic products, KJI, as negative. All right, that's pretty much it. Everything else about quaternions follows from these 9 multiplication rules. I will note in passing that what follows only works for 4 dimensions or 4 axes. If you had a 5th or a 6th, everything falls apart again like it does for 3. There is another weaker island of stability at 8 axes, 7 of which are imaginary, and these are not surprisingly called octonions. But that seems to be about it. All else is just triplet chaos on steroids. Quaternions are a special case, okay? Just FYI. Hamilton's geometric vision of his quaternions tended to consider the 3 imaginary axes separately from the real axis. This will be a recurring theme. Consider a 3D coordinate system, one in which all of the axes are imaginary, with unit vectors capital I, capital J, and capital K along each axis. Hamilton's geometric interpretation is that the rotation operator, lowercase I, rotates J into K, hence Ij equals K in the box. Likewise, the J operator rotates K into I, and the K operator rotates I into J. By substituting one equation into another, you should be able to convince yourself that this geometric interpretation is at least consistent with the 9 multiplication combinations of Ij and K I showed on the previous page. It's not a proof, it's just showing that they're consistent. Okay, that's the geometric vision. More importantly, at least for our purposes, Hamilton has to show that the results follow consistent algebraic rules as well. What rules would those be, you ask? Why, it's basically the arithmetic properties that work for real numbers and complex numbers, the commutative, associative, distributive, identity, and inverse properties. Sorry, but that's the way it is. Hamilton, by the way, deserves credit, or blame if you prefer, for recognizing the importance of these properties for evaluating consistency and practical utility of new mathematical objects. You meet these properties again and again for every new type of object that gets introduced. Vectors, tensors, matrices, the solution sets to Laplace's and Poisson's equations, and so on. So let's begin with the easy ones in terms of evaluation. Giving Q1, Q2, and Q3 defined generally as these, we first ask, are quaternions commutative under addition? That is Q1 plus Q2 equal to Q2 plus Q1? The obvious way to approach this is just simply to run through it. Because there are a lot of terms here, I'm going to show you the answer in a smaller font size. I'm also going to go through these calculations pretty quickly, but if you want to go through them in more detail, I remind you that all of these charts are available on the old Doc Goldler website. Okay, if you group the 8 resulting terms into the reals, the i's, the j's, and the k's, you can see that the answer is yes, quaternions are commutative under addition based on the fact that the real numbers inside the parentheses commute under addition. What about the associative property of addition? Does it matter what order you add them in? Following the same procedures, you can see that it does not. So, quaternions are also associative under addition. Next, within the set of quaternions, is there an object Q sub AI, AI for additive identity, such that any Q plus QAI equals itself? Yes, of course there is. It's 0 now written in this form. What about an additive inverse? For every Q in the set of quaternions, is there also an inverse of that Q? Let's call it minus Q to simplify life, such that Q plus minus Q equals the additive identity. Sure, it's -1 times Q. Multiplication. Now things get messier, and I'm going to slow down a little bit. Consider Q1 and Q2. The first question to ask is Q1 times Q2 even of the form A plus IB plus JC plus KD? This is another way of asking if the set of quaternions is closed under multiplication. Recall from the last episode that this became an insurmountable issue with triplets. I will reiterate the algorithm I used to evaluate these terms from the last episode, which I will use repeatedly going forward. Step 1 is to multiply out the terms. There are 4 terms in each quaternion, so the total number of terms in the product will be 4 squared, or 16. Messy already. I will take special care to maintain the correct order of the IJK terms since we don't know if they commute, but I can rearrange the products of the real numbers as I see fit. Step 2 is to leave the order of the product terms unchanged, but to evaluate the IJK products, paying careful attention to the sign. All right, you can see in the second group here that I've kept I the same. I times I becomes -1, I times j becomes plus k, and ik becomes minus j. All right, straightforward, albeit a bit tedious. Step 3 is to regroup the terms by their real or complex coefficients, the reals, the i's, the j's, and the k's. Here they are, and the results are encouraging. There are 4 of each kind of term, 4 reals, 4 i's, 4 j's, and 4 k's. That kind of symmetry generally bodes well. But it gets better. We can see that there are no leftover hybrid terms. Every product term is associated with a single letter if you count plus or minus 1 as a letter. Thus, we find that Q1 times Q2 is of the form A plus IB plus JC plus KD and is therefore in the set of quaternions. Unlike triplets, but like complex numbers and real numbers, quaternions are closed under the operation of multiplication. Woohoo! So with that settled, the next question is, are quaternions commutative under multiplication? Watch carefully because this is where the first plot twist comes in. No need to reinvent stuff. I evaluated Q1 times Q2 on the previous page, so I can just copy and paste. Here it is. Now, let's calculate Q2 times Q1 and compare the results. After stating the problem, I perform the following 3 steps. First, I multiply out the terms. Second, I evaluate the IJK operators. And then third, I regroup the terms into the reals, the i's, the j's, and the k's. Okay? So, are the 2 boxes the same? Do the 16 terms match up with each other? there's only one simplifying trick available to us, and that is that the four real terms of the first box have to equal the four real terms of the second box. The i's have to equal the i's, the j's, and the k's the k's. So let's have a look. Let's start with the real terms. Yes, all of these match up. A good start. Next, the I terms. Uh-oh. The first two terms match up okay, but the last two terms are mismatched in terms of sign. Positive 7 does not equal negative 7. The fact that two terms match up and two don't actually makes things worse, because it means we can't simply claim that the I terms of Q1 and Q2 are anti-commutative, okay? The I terms do not commute. We could stop here, but I'll go through the whole thing for completeness. Here are the J terms. And again, we find that some of the terms match up, but others differ by the all-important negative sign. Here are the K's, and the same issues. Bottom line, no, quaternions are not commutative under multiplication. This is the point where most mathematicians would have stopped. If quaternions are not commutative under multiplication, then they can't be legitimate mathematical objects, right? Okay, but Hamilton continued. Before I continue with the story, however, I want to point out something in Hamilton's calculations that I'm sure he was aware of. Okay, all of the negative numbers in the ijk components, okay, come from the anti-cyclic multiplication rule that he had. Here, ik equals minus j. There's your minus j. But consider, if he instead used the rule that ji equals ij equals plus k, then all four of the I, j, and k terms would be positive and therefore match up. That is, if he discovered a different ijk multiplication rule, he could have gotten quaternions to be commutative under multiplication. Why didn't he? What was he thinking? Hold that thought. Okay, this is not an ideal place to stop since we are only partway through the process of determining the properties of quaternions, but I take my self-imposed minutes per episode constraints seriously. In the next episode, we will pick up with the associative property of multiplication for quaternions and then go on to the identity and inverse properties. More plot twists await. To be continued. See you then.